Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I'm going to continue with your chapter number 7, that is linking. In the yesterday's class we have talked about the memory management, that is what is memory and how linking can be used in the memory. So today's topic is executable object file. This is the next topic, that is the 8th one, that is what is executable object file and how we are using the executable object file. But before this, let's take a quick review what we have covered in the last class, that is yesterday's class. So let's see what we have covered. In the last class, we have talked about the memory management, that is what is memory management and how we are using different memory management techniques. That is a goal that provides a convenient programming model, efficiency or efficiently allocates our memory management or scarce resources, protect the programs from each other and protect the OS from the program. We have talked about these things, that is what is the goal and how we can achieve the memory management and what are the mechanisms that we use. One of the mechanism is physical addressing and virtual addressing. Then next mechanism is your paging segmentation. We have talked about what is paging, what is segmentation in detail. Then page table management, that is how a page table is managed, and that can be managed with the help of page table management. Then we also talked about the policies, that different policies are used for the memory management, like page replacement algorithm. This is a policy that is used. Then memory and architecture. This is the diagram we have discussed. There is a processor, there is a CPU, there is a TLB, that is translation look aside buffer, there is a memory management unit, that is your MMU, that is memory management unit, there is a cache memory, disk controller, memory controller, memory. This is a memory architecture and the memory and the architecture that is used for the memory management. Then physical address, that is the address that can be used directly by the memory subsystem. That is your physical address that can be directly used by the memory subsystem. For example, we have discussed, like if there is a 512 MB of physical memory, the OS sees physical memory as an array of 512 million bytes. So this is the example, that is 512 MB memory is used as a 512 million bytes, and the first memory is denoted by the index 0, that is memory 0. Then next is your 256 into 1024 into 1024. This is what we have discussed in the last class. Then we also discussed what is virtual memory or what is virtual address. So that address that can be directly accessed by the memory, that is known as the physical address, and the virtual address is the one that is used whenever there is a requirement beyond the physical address, beyond the physical memory. That is, processes see only virtual addresses. Means only the process, not the program, not the operating system sees the virtual address, but only the process sees the virtual addresses. Then we also discuss about that how mapping is done between the virtual address to the physical address. That is how physical address is converted into the virtual address. That is, mapping is done for converting from the virtual address to the physical address and physical address to the virtual address. And physical memory is simply denoted by the MEM, that is memory, and the virtual memory is denoted by VMEM, that is your virtual memory. Then next topic what we have covered is where do addresses came from. Means what is the area, or which is the area from where addresses came from, that is the where or the place where do the addresses came from. There are three types of places from where the addresses came from. First one is your compile time. That is, addresses or the address of or physical address or the virtual address came from the or came at the compile time. That is, when the program is executing, at that time addresses came from, that is the compile time addressing or the compile time address. Then next one is your load time, that we have discussed, that at the time of loading the computer, that is converting into the bits, binary language, low level language, at that time address came from. Then next we have discussed that execution time and how addresses came from during the execution time. That is a third topic or the third point that we have discussed, from where addresses came from. Then we will discuss about the uniprogramming, that is only one program is executing at the same time. That is a uniprogramming, as the name advises, uniprogramming. That is only one program is executing at the same time. For example, DOS, that is a disk operating system, that is a uniprogram, that is a single program that is executing, that gets a fixed size of memory starting at the address 0, that is at the first address, and it gets a contiguous memory or section of memory and get the memory address or the memory size of the OS size minus the OS size. Then we will discuss about the multiprogramming, that is more than one programs are executing at the same time. That is known as the multiprogramming, and there are three concepts that is used in multiprogramming: is transparency, safety, and the efficiency. We have discussed about these three terms that is used in the multiprogramming. Then we also discuss about the relocation, that is what is relocation and how relocation is done in the memory. This is the diagrammatical representation, that is how relocation is done in the memory or how relocation is done by the operating system. This is the first physical address is the base address and the largest physical address is the limit address. Then we have discussed about the two types of relocation, that is your static relocation and dynamic relocation. Static means at the compile time or at the load time when OS adjusts the address in the process to reflect the position, that is known as the static. And once a process gets the address, it cannot be changed or it cannot be moved. Because why? The main reason is that it is static in nature. So that's the main reason why the memory is fixed or why the address is fixed. Next is your dynamic relocation. We have discussed about the dynamic relocation, that is what is dynamic relocation and how dynamic relocation is performed in the memory. That is CPU, logical address, relocation register, limit register, physical address. Then we also discuss about the advantages, that is pros and the cons of the dynamic relocation. That what are the benefits and what are the limitations of the dynamic relocation. That is the one of the main limitation is that process or the process is limited to the physical size. Why? Because there is no movement. There is no movement from one part to the another, from one process to the another process. That's why it is the main limitation. That is, it cannot share the memory. It cannot give the memory to the space. It is still or it is constant to the memory size only. Then next. We have discussed about the goals, that is what is the goals of the relocation or what is the goal of the dynamic relocation, that is transparency, safety, and the efficiency. This is the memory allocation. This is the diagrammatical representation, that is how memory allocation is performed. First of all, there is a B, that is B terminates, then D terminates or allocates the D, then A terminates. So this is the diagrammatical representation, that is how different processes will terminate and how different processes will allocate it. This is the external fragmentation, that is holes between the different processes. Then we have discussed about the memory allocation policies, that is what is memory allocation policies. One of we have discussed about the three policies, that is first fit, best fit, and the worst fit. These are the three policies that is used. This is the compaction. This is the compaction we have discussed. Then we have discussed about the next topic, another topic, that is swapping. Swapping means moving from one page or from moving from one page to the another page. That is swapping. That is move to the inactive process to the disk. That is moving the process or the moving the inactive process that is not in use to the disk, that is a magnetic disk or the optical disk, so that there is no data in the memory, or simply releasing the memory so that data will be active or data is available or memory is available for another data. That is, it moves an inactive process to the disk, releasing its memory. That is a swapping. When the program or when the process becomes active, then again reload into the memory. That is a swapping. Means first of all inactive the process, that is remove the process from the memory and store in the disk, and then when the process become active, then get it to the memory again, and then process or executes the process. Then we will discuss about the contiguous memory. Contiguous memory means that is available or that is stored one after the another. That is without any space, without any gap. There is a direct or there is a sequence of the memory that is available. That is a contiguous memory. Then we also discuss about the virtual memory. That is what is virtual memory. So whenever there is a more requirement than the physical memory, that is known as the virtual memory. That is, data is available and there is more requirement for the memory, that is more space is required, then that memory is known as a virtual memory. That is breaking the virtual memory address into the chunks of the discontiguous physical addresses. Discontiguous means there is no mandation that there is a sequence, but there is a discontiguous memory. That is one memory is located at the one part, one memory is located at the one part. That is your virtual memory. Then we have also discussed about the pages and the frames. That is, what is a page and what is a frame. So a page is a contiguous block of virtual addresses. Contiguous block means whenever we arrange the different addresses into the same sequence. Into the same sequence means line by line. That is known as the page. Then frame, it is a contiguous block of the physical addresses. So page contains the contiguous block of the virtual addresses and the frame contains the contiguous block of the physical addresses. A page is mapped to the frame. That is, a page is mapped to the or built into the frame. And that is fixed or that is fixed by the operating system. That is your 4 KB or 8 KB. Then this is the diagrammatical representation how pages will be converted into the frame. This is the logical memory. There is a frames in physical memory. Then there is a logical memory again. And the process 1 contains or process A contains 6 pages and the process B contains only 2 pages. And different operating system and the frames are allocated to the logical memory to the physical memory. That is, paging is done at the logical memory and the physical memory. Then this is how mapping is done from pages to frame. This is the mapping that is done from pages to the frames. This is the virtual memory. This is the page table. This is the frames in the memory. Then we also discuss about the mapping from the pages to the frames. That is, paging is a form of dynamic relocation where each virtual address is bound by the paging hardware. This is what we have discussed, how mapping is done. Mapping is invisible to the operating system. That is not visible for the operating system. Then we will discuss about the TLB, that is translation look aside buffer, that caches the page to the frame translation. This is the TLB that we have discussed, that is translation look aside buffer. Then how to start a process with the virtual memory that we have discussed, that is how to start a process with the virtual memory or how one process will use the virtual memory. Then we also discuss about the switching technique, that is how we can switch from one process to the another process, or how operating systems switch from one process to another process by using the concept of PCB, that is process control block. Then we also discuss about the PTE, that is page table entries, that contains more information than the address translation. That is page frame number, valid bit, reference bit, modified by protection. Then we also discuss about the multi-level paging. Then we will discuss about the sharing also, that is how sharing is done in the operating system so that memory will be shared by the operating system. Then we will discuss about the summary, that is what is the summary that we have discussed about the page. This is what we have discussed in the last class. This is a session for the yesterday's class. Now next session is today's class, that is the today's topic, that is executable object file. This is the main topic. This is our today's topic, that is executable object file. This says we have seen that how linker merges multiple object module into a single object file. we have discussed in the first class, that is how multiple or how different multiple object module, that is how multiple object modules are linked together into a single executable object file. A C program which begin life as a collection of ASCII text files has been transformed into single binary file that contains all of the information needed to load the program into the memory and run it. Figure 11 summarizes the kinds of information in a typical ELF executable file. This paragraph says, we have already discussed that how multiple object modules are converted or combined into a single executable file, and how memory will load the, or how it will be loaded into the memory and then run it. That is your executable object file, and that information is available in the ELF executable file. And this is the diagram, that is ELF executable file. First of all, there is a ELF header, then there is a segment header table, that is your how segment will be maintained or how different parts will be maintained in a header or in a executable object file, that is your segment header file. Then there is a information about the header file, or there is the information about the process, that is it contains multiple extensions, multiple files, multiple process. First one is your .init, that is .init. Then next is your .text, that is your text file. Then .ro data, then data, simple data, then .bss, then .sym tab, that is a symbol table. That then .debug, then .line, then .str tab, then there is a section header table. So there is, first of all, there is a ELF header, then there is a segment header table, and then there are multiple parts of the segment header table, and at last again there is a section header table. So these are the topics, or these are the content that is available in the executable object file that is covered in the ELF executable object file. So this is a diagrammatical representation, that is how executable object file is formed and what is the content of the executable object file. This says the format of an executable object file is similar to that of the relocatable object file. As I told you, there is a format that is available. This is the table, that is a format. The ELF header describes the overall format of the file. It also includes the program entry point, that is what is the entry point from where the program begins, which is the address of the first instruction to execute when the program runs. The .text, the .ro data, and the .data sections are similar to those in a relocatable object file, except that these sections have been relocated to their eventually runtime memory address. This is the .text, .ro sections are similar to the programs in the executable file. The init section defines a small function known as the init, that is the first function that is used for the initialization part. As the name advises, .init, that is the initialization. So whenever there is a requirement for the initialization, that is a program initialization code that is done by the init section. Since the executable is fully linked, it needs no .rel section. That is, once the executable file is fully linked or it is fully relocated, then there is no requirement for the .rel or .rel section, that is relocated section. ELF executables are designed to load into the memory. That is this or the ELF headers or the ELF, there is a requirement of the ELF that is used or designed to easily load into the memory with contiguous chunks of the executable file mapped. This mapping is described by the segment header table. So this is the segment header table that is used for defining or for use for the mapping purpose. From the segment header table, we see that two memory segments will be initialized with the content of the executable object file, that is line 1 and the line 2. So this is the diagram that shows the executable object file. This is the executable of object file that contains the whole information. This is a segment header table that contains the multiple information. Now let's see with the help of PPTs. This is executable and linkable format. This is the outlining what we have covered in the today's class with the help of slides. That is, what is ELF, what are the basics of ELF, executables of the ELF, linking view, execution view, then example, and then loading and executing the and ELF executables, then various types, then at last conclusion. So starting with the what is ELF. It stands for executable and the linking format. As I told you, it standardizes the executable file format used in most Unix system. That is, it provides the standard for the executable file, so that executable file will be used and the object file will be used. That is, maintaining the standard for the executable file format, or maintaining the standard for the executable file that is used in most of the Unix system. Then it substitute of the traditional A dot due to the efficiency issues. Its substitute means it ELF updated the or replaces the A dot out option, that is your A dot output file, that is a relocatable file, due to the efficiency issue. There is a limitation of the efficiency, or there is an inefficiency. That's why it replaces, or ELF replaces the traditional A dot out. That is where it replaces or it maintains the dynamic linking. So it replaces the static linking. Then it is developed originally in the Unix System Laboratory, that is USL, and adopted by the TIS, that is your Tool Interface Standard Committee. So ELF is developed or originally developed by the Unix system and maintained and controlled and adopted by the TIS, that is Tools Interface Standard Committee. Then these are the basics, that is what is the ELF object file, or what are the types of ELF objects file. That contains three parts. One is relocatable files, one is executable files, one is shared object file. Now what is relocatable object file? That have a extension .a, that is your relocatable object file, that is a code and the data to be linked with the other object file. So any code, any data that is used to be linking, or that is used for the linking with the other object file, that is known as the relocatable object file. Then next one is your executable files, that is the file that is used for the execution. That is, whenever we convert the number, whenever we convert the data into binary file, that is done by the, or that is known as the executable file. Means a executable file is maintained whenever we compile the data. Compile means whenever there is a compiler that converts the high level language into the low level language, that is bits, that is done by the compiler, and then a file is maintained, then a new code is maintained, that is known as the executable object files. Then next is your shared object files, that is how different files will be shared, or how different files share their objects. That is your shared object file that contains the library. That is, there is only one library that is used that contains multiple functions. For example, in C there is a printf, there is a scanf, that is shared by the multiple objects, that is known as the shared objects file. For example, there is a file that is known as the a.a, that is a shared object file that contains multiple options, multiple libraries, multiple library function. For example, printf, scanf. So that is known as the shared object files. Next is your object file. Means what is the object file? As I told you, there is object file whenever we convert the high level language program or any program into the binary representation, that is known as the object file. That is binary representation of programs intended to execute directly on a process. That is, first of all, whenever we convert the high level language into the binary level language, that is a new session is maintained, a new file is maintained. That file is known as the object file. That is a binary representation of the program that is ready to execute, or that is intended to execute directly on a processor. Means there is no requirement for convert it into the bits. It is already in binary form. That is a object file. Now, what is the executables? This is the object file. Next, executable files. That is, it contains two types of executables. One is static executable, one is dynamic executable. Static executable is self-contained. Self-contained means that is a self-contained file that contains self-contained code that is used for the library codes. For example, two large files due to the static inclusion of library code, that is your self-contained. Next, dynamic, using external code or data at runtime, that is it uses the external code or the data at the runtime, that is your dynamic executable. That is more convenient to use, that is a more convenient way to use. Then two views of executables according to their participation. That is, what are the two views that is available, or what are the views that is available according to their participation. There are two types of views. One is linking view, one is execution view. Now, what is linking view? That is executable participation in the program linking. And execution view is executable participation is in program execution. That is, whenever a program is executing, or whenever there is a view when the program is executing, that is known as the execution view. And before the execution, the program is converted into the bits, that is known as the linking view. Then this is the comparison between the linking view and the execution view. That is, this is the linking view, this is the execution view. First of all, in linking view there is a ELF header. Then in execution view again ELF header. In linking view there is a program header table, that is optional. In execution view there is a program header table, that is not optional. So this is the comparison between the linking view and the executable view. There are the two types of the executables. So in executable file there is a program header table, that is not optional, but in linking view it is optional. And the first field is same, that is your linking view, or that is your ELF header. Then there are multiple sections in the linking view. These are the sections, that is section 1, section 2, section 3 up to section N. And there is the execution view, that is segment 1, segment 2, segment 3 and so on till segment 9. Then there is a section header table. This is not optional, this is mandatory in the linking view, but it is optional in the execution view. So these are the comparison, that is how execution view and the linking view is used at the executable between the different views, or between the executables. Now, next is your link view, that is used at the static linking time for relocating the file combination. Execution view, that is used at the runtime to load and execute the programs. Then there is a ELF header, as I told you, describes the file organization and resides always at the beginning. So it shows the file organization, that is how file will be organized, and it always decides it is available at the top of the table, or at the top of the place, that is your ELF header. Then next is your program header table, that is if present tells the system how to create a process image. That is, the program header table is used to tell the system, or to know the system how to create a process image. Then next, section header table, if present, contains the information describing the file section. So there are multiple sections that is used for the different tasks. That is section header table, that is your program header table, that is your ELF header. Relocatable files have section header tables. Executable files have program header table. There is a difference again, relocatable file and the executable files. Share object files have both the tables, that is a section header table and program header table. Then next is your linking view. In detail, that is what is linking view and what is executable view. In linking view, it says it divides the object file into a collection of sections. That is, in linking view there is a division, or object files is divided into the multiple collection of the sections, into multiple parts of the section. Sections have their names, their types, their memory allocation or memory location, or permission. So this is the section that is used in the memory allocation, that divides the object file, that divides the multiple object file into the one. So sections have name, type, requested memory location, permissions. And each section contains a single type of information and can contain flags. Flags means writable data, memory size during the execution or executable machine instructions. So linking view divides the main object into a collection of sections. For example, if I'm using the object file that is a.out, that is divided into the collection of sections into collection of parts, that is known as the that is done in the linking view, and each section have a name, type, requested memory, permissions. These are the important sections that is used, that is divide the main object into multiple sections, that is this part. Important sections are, first of all, there is a .interp, that is your interrupt, that contains path name of program interrupter, that is your dynamic linker, that is your interrupt. Then there is a .text, that is your code of a program. Then .data, this is the initialized data. Then there is a BSS, that is the uninitialized data. So there is a difference between the data and the BSS. Data contains the initialized data. For example, if I'm writing the C program and if I'm initializing my variable, for example, int sum equals to 0, that is it is stored in the .data file. And whenever I only initialize the data, but I only declare the variable, not initialize the data, that is not equals to 0. But if I only using that int sum, that is your initialized data, and that is stored in the BSS. So initialize means assigning the value, uninitialized means only declaring the variable and not initializing the value or not using the any value, that is 0, 1, 2. Then next is your .init, that is executable instructions for program or process initialization. That is, init contains the executable instruction for program initialization. Then FINI, that is used for the process termination. That is, if the init is used whenever there is a process initialization, whenever there is a starting of the process, or whenever the process is started, that is your process initialization. Then process termination, that is it is used for the FINI, that is process termination. Then PTL, that is hold the procedure linkage table, that is your PTL. Then RE.X, that is relocation information for the section X. Then .dynamic, that contains the dynamic linking information. So these are the important sections that is used in the linking view, that is contained in the ELF header, or that is contained in the ELF. Then next is your execution view. This is your next part or next view, that simple or view that divides the object file into the segment. That is, it is a simpler view that divides the object file into multiple segments. And the linking view, in comparison, linking view divides into multiple sections, and this divide into multiple segments. And the segments have simple type, requested memory location, permission, size. So segments have a different categories like simple type, requested memory location, permissions, and the size. Size in terms of the file, size in terms of the memory. And the all loadable sections are packed into the segment so that file mapping is easy or easier. So all the loaded sections are packed or assigned into different sections so that the mapping is easier and the file mapping is easier than the previous one. That is your segment. This is the segment types. There are two types of segment or that contain segment. One is your interrupt, that is your interrupt. That is pointed to the dynamic linker for this executable. That is point to the dynamic linker that is used for the executable. That is contained in the .interrupt section. That is used for the interrupt. For example, if I am executing the C program, then simple C program is executing, but suddenly my variable is not declared or my variable gets new value. That is, there is an interrupt because the program is running up, and then there is a hangout, that is it gets a new value, that is the interruption takes place. So whenever there is a disturbances in the program, that is known as the interrupt. So if there is an interrupt that is stored in the interrupt file, that is stored in the interrupt segment, that is of, or that is a part of the execution view. Then next segment type or the next part of the segment is your dynamic, that points to the, or that is used as a pointer to the dynamic linking information, that is dot dynamic section. This is the example that is used. One is relocatable file 1, that is int x equals to 5, int main, that is first of all declaring the values to the 5, that is x is the variable, that is initialize the value with the 5, then int main, then curly braces start, int r equals to x plus function, that is r is also a variable that is declaring the variable, or that is used as the x, and again using the function, or again adding the function with the plus function. Then the next is your exit 0, that is at the exit 0, then there is a curly braces close. So this is a relocatable file 1, that is initializing the variable as a 5 using the main function, then using the function, that is in incrementing the function to the, or the declaring the function and adding the value, that is 5. So it is 5 plus function, then int r, that is r is a variable that is of int type. Then next is your relocatable file 2, that is int v equals to 10, that is v contains the value 10, u contains the value 32, and there is a next variable that is your z variable, that is now there is a difference. Now you see the difference. These are the initialized variables, that is initializing the values, and z is an uninitialized variable that is not initializing the value but only declaring the variable. Then using the function, that is int function, curly braces open, return v plus u, that is it is a function that returns the value, that is 42, that is 32 plus 10, that is the 42. Now relocatable object files. This is a relocatable object file. There is a system code, system data, there is a main function, the same example. There is a main function, there is a x equals to 5, there is a function declaration or definition, that is it contains the value as v equals to 10, u equals to 32, and int y. So this is the declaration part, and that will be converted into the next part, that is the headers. There is a header part, there is again the system code, there is a main function, there is a declaration that is stored in the .text file. Till this it is stored in the .text. Then next is your data part, that is stored in the .data. Next uninitialized data. So this is z is your uninitialized data that is stored in the .bss, and this is your initialized data that is stored in the .data file. Now you understand what we have covered. This is the diagrammatical representation, and this is stored in the .text. This is your first part, main a system code. Then system data, that is x5, v10, u32 uninitialized data that is stored in the .data, and then there is a other part. Next, this is the loading and executing and ELF executable. So this is the next file, how we can load and how we can execute, and at the same time how we are using the ELF executables. These are the points that is followed, how different loading, execution, and the ELF executable is performed. First of all, first point says open the file. That is open the file. Then next, map the load segment into the memory. That is mapping the load segment, that is mapping or from virtual address to the physical address, that is mapping the load segment into the memory. Then call the dynamic linker specified in the interrupt segment, passing the information about the executable. That is call the dynamic linker, that is make the calling, that is called with the help of a dynamic linking specified in the interrupt segment, passing the information about the executables. This contains multiple parts, that is how calling is done and how interrupt segment is not followed, and pass the information about the executable. First point says it handles or handles all the dynamic shared library needs of the executables. That is shared all the needs or shared all the or handles all the dynamic needs of the executable. Then next point says retrieve information from the dynamic segment. That is retrieve the information about the dynamic segment or from the dynamic segment. That is retrieving the information at the dynamic level, at the moment level, that is a dynamic segment. Then next, load all the required library into the memory. So this is the next point. That is then after retrieving the dynamic allocation, after retrieving the dynamic segment, then loads the required library into the memory. That is loading the required functions, loading the required library functions like printf, scanf into the memory. Then modifies the executable. That is, if there is a requirement to modify the executable, that is .out file or .a file, then simply modifies the executable so that it can access needed resources to the in the libraries. That is, if there is a requirement to modify printf, scanf, then simply modify the executable so that it can access or it is easy to access the needed resources. This is basically what we have covered. This is relocatable file 1, relocatable file n. That is any types of relocatable files, then that is combined or that is used or that is combined by using the static linking, that is converted into the executable object file. So first of all relocatable files, then executable object files, then next is your dynamic linkers, that is used by the shared libraries. Then next is your executing, then executing the programs. So first of all there is a relocation or relocatable files and number of relocatable files, then static linking, that is or that gives the executable object file, then shared library is used and then that is converted or that is going into the dynamic linker, then executing, that is executing the code. So this is how load, how execution and how ELF executable are used into a single object file. Next, various parts, that is what are the various parts that is used, that is shared libraries need to be compiled memory position independent. That is, it needs to be compiled during the memory, that is done by the PIC, that is memory position independent or the position independent compilation. Uses a GOT, that is global offset table with the pointers to the variable created at the compile and the runtime. Then next uses the procedure linkage table, that is your PLT for the procedure library calling. That is this is the shared library. First of all uses the GOT with the pointers at the compile time and the link time. Then uses the PLT, that is procedure linkage table for the procedure library calling. Then implies some performance disadvantages, that is implies the performance disadvantages, that is again the new feature or that is also covered in the shared libraries. Then others means what are the other part that is available, that is relocation tell dynamic linker. That is what is relocation? That tells the dynamic linker to rewrite parts of the executable to refer to the external resources. So this is what we have covered in the last class. Relocation, that is mapping is done, that tells the dynamic linking to rewrite the code, to rewrite the different parts of the executable that refers to the external resources. And exists a dynamic debugging structure. What is a dynamic debugging structure? Means dynamic debugging or error finding is done at the dynamic level that offer the various information about the process memory and the binary loaded. So this is the conclusion what we have covered, that is logical evolution of the old executable formats, convenient double view depending for the linking and the execution time, great support, convenient separation, standard and defined functionality. Now let's see with the help of your book. This is the same line, that is data segment dot data what we have covered, that is initialized data, but when there is an uninitialized data that is stored in the .dss section. Next, how to load the executable object file. That is, to run an executable object file P, we can type the name to the Unix shell command line. This is the way how we can load the executable object file. This is a huge topic, long topic that we will cover after a short break, that is 5 to 10 minutes break. So first of all, take 5 to 10 minutes break, then come back, then starting with the topic, that is loading the executable object files. So let's take 5 to 10 minutes break. Now let's start with the next topic, that is loading executable object files. Till now we have covered what is executable object files. So next topic is how to load the executable object files. This says to run an executable object file, for example P, we can type the name to the Unix shell command line, that is Unix, then there is a symbol that is used, then there is a dot, then there is a slash, then there is a object file name, that is your P, that is your executable object file. This says since P does not correspond to a built-in shell command, the shell assumes that P is an executable object file which it runs for us by invoking some memory resident operating system known as the loader. This point says, or this line says, that it does not correspond to a built-in shell command, but it assumes P as an executable object file. Executable object file which it runs for us for invoking some memory resident operating system code known as the loader. So loader is used to load to the operating system, load to the Unix shell command, so that Unix can interpret the command and load the executable object files. Any Unix program can invoke the loader by calling the execve. So this is a function that is used to load the program, or used to call the program, or load the program by using the function that is known as the execve. The loader copies the code and data in the executable object file from the disk into the memory and then runs the program by jumping it to the first instruction or the entry point. As I told you, all the entry point instructions are stored in the .init file. So this is used whenever there is a loading part. That is, first of all, it will copies the data, or the loader copies the data from the disk to the memory, and then runs the program by jumping to the next instruction or jumping to the first instruction or the entry point instruction. This process of copying the program into the memory and the running is known as the loading. That is, first of all, copy the program, or getting the program, collect the program, load the program, or the copy the program into the memory, that is loads into the memory, and then run it with the help of the executable files, that is known as the loading. This is loading is done. That is, first of all, collects the data, then copies the data into the memory, and then run it, that is known as the loading. Every Unix program has a runtime memory image similar to the one in figure 13. This next is figure 13. This is figure 13. This is how loading is done at every level, in the shell program, in the C program, and any program. This is the Linux runtime memory image. This is the kernel memory, that is memory invisible to the user code. Then there is a user stack that is created at the runtime. Then there is %ESP, that is your stack pointer. This is the arrows that is used. Then memory mapped region for the shared library. This is the memory mapped region that is used for the shared library. Then there is a space, or there is a vacant position. Then empty position. Then there is a runtime heap. Runtime heap means that is created at the runtime, that is also known as the malloc. So malloc is a function that is used at the runtime. Then read-write segment, that is next is your read-write segment. That is how we can read the data and how we can write the data. That is your .data part and .bss part. First is your .data part, that is used for using the, or for writing the uninitialized variable, and .bss is used for the .data is used for the initialized variable. That is, whenever we initialize the variable to some value, that is stored in the .data file, and then whenever we are using uninitialized variable, that is only declaring the variable that is stored in the .pss part. Then next is your read-only segment, that is your next part, that is also loaded into the or loaded from the executable file that contains .init, that is the first information of the information about the first process, that is the initialization process whenever the process initialized. Then .text, that is used as the storage of the text, that is a string of characters. Then arrow data. So this is the read-only segment, and prior to this there is a read-write segment, then runtime heap. So this is loaded from the executable file. So this is how we can load or from the executable file, that is load from the executable file. Then these are the file. Then runtime heap, that is a memory allocated or stored in the memory at the runtime, that is your runtime heap. Then there is a up arrow, then memory mapped region for the shared libraries, then there is a up arrow, then there is a user stack, then there is a kernel memory. So this is how we are assigning or how we are using the different memory process, and how we can load or how computer load the executable object file. So this is the structure how executable object file will be loaded. So this is the format that is used. Every Unix system program has a runtime image similar to the one in the figure 13. This is the image that is used by every program that has a runtime memory. On 32-bit Linux system, the code segment start at address 0 or at address 0 into 080. The data segment follows at the next 4 KB aligned address. The runtime heap follows the first 4 KB aligned address. This is says with the different margins with the different arrows. That is how or who follows which one. That is the which is the first part, then next part, then next part. This shows the, or these lines shows the various alignment or various flow, that is from where data will be flow. This is the important point, that is the data that is resides in the memory part of the operating system known as the kernel. So kernel is a memory where the data is stored of the operating system. That is the memory resident part. When the loader runs, it creates the memory image shown in the figure 13. That is when the loader runs, it creates the image that is shown by figure 13. This is the figure 13. That is how memory management or how a loader runs or creates the memory image. Guided by the segment header table in the executable, it copies the chunks of the executable into the code and the data segment. That is, whenever the loader runs, whenever there is a loader requirement, it creates the memory image. That it guided by the segment header table in the executable, copies the chunks of the executable into the code and the data segment. Next, the loader jumped to the program entry point. So this is jumped at the program entry point, which is always the address of the start symbol. The startup code at the start address is defined in the object file, that is control.o, and is same for the C program. Then the startup code at the start address, that is at the starting point, there is a start address that is defined in the object file, that is the object file that is known as control.o. Why it is .o? Because it is an executable file, and that executable file object file is always have extension that is .o, and control is the name of the object file, and is the same for all the C programs. Figure 14 shows the specific sequence of calls in the startup code. After calling initialization routines from the .text and .init section, the startup code calls the @exit routine. That is, first of all, there is a start address, that is this address, that is defined in the control O. Then shows, or the next figure shows the sequence of call. After calling initialization, that is after initializing the values or the routine from the .text and from the init section, The startup codes calls the at exit routine that is used for the exiting the application, that is used for the ending the application, which appends a list of routines. Appends means which updates or add the list of routines that should be called when the application terminates normally. That is, it adds or appends the list of routines that is called or that should be used when the application terminates normally. That is, if the application is running smoothly and at last terminate normally, then it appends or add the values to the routine. Next, the exit function is registered at the or by the at exit function and then returns control to the operating system. So this is the code that is used for in the C programming language or in any object programming language that uses the object file for writing the program, for initializing the programs. This is pseudocode for the control or startup routine in every C program. That is how this is the procedure how a C program will be executed. That is the starting point, initialization part, and then there is a exit point. So first of all, call library C init first, that is startup code in the dot text. This is the starting point that is denoted by the address, that is underscore start address. This is the underscore start address. Then there is a call, that is a library C. Then there is a init function and there is a first function. This is the function that is used, that is library C init first. Then there is a call function, that is the next function, that is call init, that is the startup code in the init function. Then startup code in the dot text function, that is call at exit. Then call main, that is application main routine, that is your call main, that is used for the calling the main function. This is used for initialization. This shows that it is exit, that is the startup code for the exit point. Then there is a main function that contains multiple values, declaration, functions, function definitions, that is called at main function. And then at last there is a exit function that returns a pointer, a control, or that returns a control to the operating system. That is, control is again passed to the operating system. That is called exit. Next, control never reaches here. That is at 7 point, control never reaches. Why? Because at the 6th position, that is call exit, it exits a call, that is it moves the or returns the control to the operating system. So this is how exit function is used. Next, the startup code calls the application main source which begin executing the C code. That is, it is the startup code that the main function is using or executing the C code. After the application returns, that is after the application finishes or returns, the startup code calls the underscore routine. That is, it calls the next function, that is end function, that is underscore routine, exit routine, which returns control to the operating system. So this is the representation how controlling is done and how program flows in the any programming language, that is for example C. So this is the start phase, this is the initialization, then initialization phase, that is the exit, that main function, then exit function. Now let's see with the help of PPTs. We will discuss about the ELF, that is executable and linkable format, that is your ELF. That is stored or it is a standard binary format for the object file. As we discussed, it is originally proposed or originally developed by the AT&T system Unix or vUnix, then adopted by the Unix system. So it is first adopted or developed by the AT&T, then it is then adopted by the or used by the Unix system. One unified format, or that is one unified format for this one is or the different types of executable files are relocatable object file that have extension .o, executable object file that have extension .out, and next there is a shared object file that have extension .so. Generic name, what is the generic name that is used? That is your ELF binaries. Then this is the ELF object file format as we have discussed. First of all, there is a ELF header that contains a number, type, machine, byte ordering, etc. Type means there is a .o file, .executable file, .so file. That is your source file. That is a shared file, not source file. Then there is a program header table that is required by the executables that contains multiple information like page size, virtual address, segment sizes. Then there is a text section that contains a code. There is a data section that contains the initialized data. Then there is a BSS that contains the uninitialized data. Then symbol table that contains the symbol table or the symbol table. Then rel.text data that is used for the relocation for the text section. Then rel.data section that is relocation for the .data section. Then debug section that is information for the symbolic debugging that is used, for example, gcc-g, that is the debug section. This is a table that is ELF header, program header table, text, data, BSS, symbol table, REL text, REL data, debug. Then overview of the source translation. That is how translation is done. That is overview of the source translation. First of all, there is a user created file. So these are the user created files. That is a make file, CC++ source and header files. Then there is an assembly source file. Then there is a linker script file. So these are the user created file that is used by the or created by the users. Then there is a make utility. This is compiled by using the make utility. This is compiled by using the compiler, preprocessor, assembler. Then there is a linker script that is used for the linking. Then after compilation and the assembler, that is converted into the object file. Then there is the archive utility that is used for getting the library files. And these are the multiple files that is used, that is shared object file, linkable image file, executable image file, link map file. This is how translation is done in the operating system. Then next is your executable versus linkable. As we have discussed, there are two types of views. One is executable view, that is executable file, and one is linkable file. This is the program head table. This is the optional in this, and this is optional in this, as we have discussed. Then what is the role of the linker? That is, what is the role, why linking is done? That is used for mapping the different sections into different segments. That is, section 1 data is mapped to the segment 1. Section 1 data is mapped to the segment 1. Section 2 data is mapped to the segment 2. Section 2 data is mapped to the segment 2. This is the linkable files. And then there is n number of segment, n number of sections that will be segmented, or that will be mapped to the different n number of segments. Then this is the ELF header that contains these types of information like e-type, e-machine, e-version, e-entry, e-fof, e-shof, e-flag, e-size, e-parent size, e-phenum. These are the variable that is used. Then there is a section header. That is a section header. In section header, this is the these are the variable that is used, or these are the point that is used. That is sh name, sh type, sh flags, sh address, sh offset, sh size, link, info, address align, then entity size. So these are the different section header that is used in the program. Then there is a program header that is used, that is p type, p offset, p vertical address, ppv address, file size, memory size, flag, alignment. Then executable, or loading the executable object file. That is how to load the executable object file. This is the same table, that is your executable object file. This is the syntax that we have used, that is how to load the executable object file with the help of book. So this is what we have covered with the help of book. We have discussed about with the help of book. There is unused data, then read-only segment that contains innate text RO data, then read-write segment that contains DSS data.bss. Then there is a runtime heap that is created by the memory that is available at the runtime. Then in this there is a break. This is a break section, and these are the loaded from the executable file. That is, it loads from the executable file. Then there is a gap that shows with the help of arrows. Then memory mapped region for the shared library. So this is the memory mapped region where the mapping is done between the virtual address and the physical address. Then again there is a space, there is a vacant position, there are two arrows used. Then there is a ESP, that is a stack pointer. Then there is a user stack that is created at the runtime. That is created at the runtime means whenever there is a execution phase, whenever we compile the data, whenever we run the data, at that state there is a user stack. Then there is a kernel virtual memory, that is memory invisible to the user code. Then these are the executable, or how to load the executable object files, that is used by this syntax, that is using the dollar, that is a.out or $exe. Then invokes the exe function. As I told you, there is a function that is used for loading the executable file that is known as the .exe that is the exe executable ve function or system call to invoke the loader. Then next, loader copies the executable object file, that is, it loads the or copies the executable object file from the disk to the memory and run it from its entry point. So this is how it will load. First of all, uses the $a.out, then it load into the memory or invoke the function, that is executable ve function, then loads the memory or loads the program into the memory and run from the starting point, that is your entry point. This is the diagram how loading will be done. So that's all for today's section. Thank you so much everyone. Now if you have any questions, then please text the questions. Now let's see with the help of PPTs. This is finished. This is finished. Yeah, this is the important point that is left. How do loader really work? This is the important question. This says our description of loader or loading is conceptually correct, but intentionally not entirely accurate. This is the important point. That is, intentionally it is correct, but not that is logically it is correct. That is conceptually, that is theoretically it is correct, but conceptually it is, or intentionally it is not entirely accurate. To understand how loading really works, you must understand the concept of the different processes. That is, you must have a knowledge of the different processes, virtual memory and the memory mapping, which can be discussed, which can have not been discussed. Yes. So this says as we have used different concepts like processors, virtual memory, memory management, memory mapping. So this point says, or this line says, loading is done before or to understand how loading really works, to understand the concept of different processes, virtual memory and the memory mapping, which have not discussed yet. So it is no point to discuss with the loader, or it is no point to use with the loader. Next is your dynamic linking with the shared library. That I will discuss in the next class, because there is no time left. It's for 5:50 as per IST. So, and this is I will discuss in the next class, that is dynamic linking. That is how the linking is done dynamically with the shared libraries. That is where how different shared libraries will link with the one another. And tomorrow this chapter is will be over. That is it contains, or it is only 2 topics that is left. So tomorrow I will finish this chapter. That is 2 or 3 topics that is left is over in the tomorrow session. So today is the last class for this topic or for this chapter. From day after tomorrow, I will be starting with the next topic, next chapter, that is chapter number 8. So that's all for today's session. Now, if you have any doubt, then please text the doubt and I will answer you. But before that, let's take a quick review what we have covered in the today's class. We have started with the ELF. That is, what is ELF? That is executable and linkable format. We have started with different basics, different concept, executable, linking view, execution view. Then we have discussed what is the full form of executable, then theory of the executable, that is it first developed by the Unix system, then it is used by the A.out, then it is developed, adopted by the Unix system and adopted by the TIS committee. Then we have discussed about the types of ELF object files, that is relocatable files, executable files, and the shared object files. Then we have discussed about the object file, that is binary representation, that is in bits term, that is your binary representation. Then we have discussed about the static versus dynamic library, that is what is static library, what is the static executables, what is the dynamic executables. Static means that is self-contained, or dynamic means using the external code or the data to the available at the runtime. Then we also discuss about the two views about the executable, that is linking view and the execution view. Then this is the comparison between the linking view and the executable or execution view. This is the link view that is used at the static time linking. Execution view is used at the runtime. Then we will also discuss about the ELF header that is used that describes the file organization. Then we have also discussed about the program header table. What is program header table? What is section header table? What is relocatable files? And what is executable files, shared files, or how shared file contains multiple data, table data. Then I have also discussed about the linking view, that is what is linking view, how the different linking view can be done, that is it divides the object file into different sections, that is a linking view, and section contains multiple parts like name, type, requested memory location, permissions. This is the important section that is available in the linking view, that is .interrupt, .text, .data, .bss, init, fini, ptl, re, dynamic. Then we also discuss about the execution view, that is dividing the data or the object file into different segments. So linking view is dividing the files into different sections, and execution view is to divide the file into different segments. Then we have also discussed that segment contains a simple type that is available at the type. Then we will also discuss about the different execution view types, that is segment have a different types, that is segment type, simple type, permissions, sizes in files. Then we have discussed about the segment type that is used, that is .interrupt, that is .dynamic, that is used. Then we also discuss one example, that is how relocatable file will be used. This is the best example for showing the .dss, bss, .data, initialized web variable, uninitialized web variable, and this is the diagrammatical representation, that is how data will be available or how different data will be available. So we have discussed about the relocatable files, system file, .text files, .data, .bss section. Then we also discuss about how to load and execute the ELF executable file. These are the multiple steps that we have discussed, and this is how to load the relocatable files, executable files, shared libraries, and the dynamic libraries. This is the various files, that is the shared library that is used, that is PIC, GOAT, PLT. Then we also discuss about the different relocation techniques, that is how relocation can be done, and then there is a dynamic debugging structure. Then we will conclude that what we have covered in the last class, or what we have covered in the today's session. So that's all for today's session now. Now, if you have any doubt, then please text the doubt and I will answer you. In tomorrow's class, I will be starting with the next topic, that is dynamic linking with the shared library. That is how dynamic linking is done with the shared library. That is the shared library that is available for all the concepts, and how it is linked with the dynamic at the dynamic time, that is at the runtime. So this is what we have covered in the tomorrow's class. So that's all for today's session. Thank you so much everyone. Now if you have any doubt, then please text the doubts.